Okay, another application of Faraday's law is the generator, and this is how it works. I want to tell you how it works. So if you have a magnetic field in the red, and you have a coil of wire, by spinning that wire in that magnetic field, you are changing the magnetic flux through that hoop. And so because you're changing the magnetic flux, in the hoop will be induced an EMF and if it's connected to a complete circuit, a current in the wire. So what you're doing is you're taking mechanical energy, the turning of the hoop, and you're turning it into electrical energy. So let me detail how that works. Okay, so here is a side view of the hoop. So like if this is the hoop and the field is heading that way, then this one is going to look like that. So it's straight on. Whereas the hoop is rotating then, and it's rotating about this axis. So it's rotating like this, like that would be that hoop then. You see how that's that hoop? And then it rotates like that. So the hoop is rotating around like such. Now, so it's got the most flux through it this way, and then it's only got a part of that flux this way. And now there's no flux, because you see how there's nothing there's nothing going through this window this way. All the field is that way. Okay, so but you're turning it with a constant angular speed, and so omega, that W is an omega, and that's to show that's the speed at which you're turning it. Okay, so before we go any further, let's just talk about the flux then. The flux, the field is going to be uniform, and the flux is just going to be this then. The magnetic flux, B, is going to be the B dot A. Now, is the B changing? No, the B is always uniform in my setup. Is the A changing? No, the area of the hoop is not changing. It's always the same area. What is changing is the orientation that the hoop makes with the field, and so that's how you're changing your flux. And so I want you to see that in this case, the A will be this way. That's the A vector. It's in the same direction as B. But in this one, the A vector is this way. So A is this way. That's the A vector. And here's the B vector. And so what you need to do is you need to only take, what the dot product says is take the part of B that's in the direction of A. Or you can do the other, take the part of A that's in the direction of B. But if this is theta, if that angle is theta, then if I only want the part of B that's in the direction of A, that might be this part. And that part, to get this component of B, that is B cosine of theta. So that's going to be B cosine of theta times A. That gives me the same thing. Remember that this is a scalar quantity. So what we're going to take from this sheet here is that the magnetic field, I'm going to say, is just going to be B times A times the cosine of theta. It's the theta that's changing. Okay. So if that's the case, then the EMF that's induced in this hoop is going to be equal to negative N, depending on how many hoops we have, times how fast the flux is changing with time. d phi dt. And so, but remember that the flux, the magnetic flux, is going to just be B A cosine of theta. Now, something about theta. Theta is related to omega in that, you remember when something is rotating, the angular speed, the average angular speed is delta theta over delta t. Well, we can make that delta theta, we can make that theta final minus theta initial, and t final minus t initial. But what if t initial is 0 and theta initial is 0? So I'm going to make these 0, get rid of them. And so omega is theta final over time final. And if I bring the time final on the other side, theta is just going to be equal to omega times t. Omega times, if you want to know where it's going to be at in its rotation, just multiply the t times omega. Okay, so my flux is going to be equal to B times A times the cosine, and I'm not going to write theta this time, but I'm going to write omega t. Okay, well that's what's going to go into here. So I come on over here, and I'm going to say that the EMF induced then is negative n, the derivative with respect to time, of the flux. Now this is the flux over here, B A times the cosine of omega t. Okay, well, it turns out that the B and the A aren't changing with time, so I can bring them outside of the derivative. And so when I take this derivative then, the cosine of omega t, using the chain rule, I'm going to get this. It's going to be negative n B A, and then I'm going to get, when I take the derivative, it's going to be an omega times the sine of omega t. And that's going to be a positive now, because the derivative of a cosine is a negative sine. Okay, so that's the EMF that's induced. And I'm going to rewrite that just on its own sheet of paper, and then let's see if we can make sense of it. So coming over here then, the EMF that's induced by spinning a bunch of coils of wire through a magnetic field, the EMF that's induced is going to be equal to, just writing it all out. I'm going to actually write it a little differently. It's going to be, I'm going to write it as WNBA sine omega t. And so the reason I wrote that a little differently is because WNBA sounds like the Women's National Basketball Association. It's just a nice way to remember it. And so I want to just make a little sense of this. So how do I get, when I'm turning a generator, a handheld generator, let's say, how do I get the biggest EMF possible? Well, there's a few ways that I can up the amount of EMF. One is I can turn it faster. So remember, if you turn it real fast, the light bulb for our generator would light. The light bulb that the generator was connected to would light even brighter. Or I could add the number of turns. So if I increase the turns from, like, say, 1 or 2 turns to 100 turns, then that boosts up the EMF as well. Or I could make the magnetic field that it was spinning in, I could make that bigger. Or I could make the area of the hoop bigger. I could just make the actual area of the hoop bigger. So all those different ways I can change the EMF. But if you notice, if I were to plot EMF versus time, it's a sine wave. And so it's going to be going something like this. And its maximum is going to be at WNBA sine theta, or WNBA. That will be its maximum. And its minimum will be negative WNBA sine theta. That's if I'm turning with a constant omega. So you're not generating constant power, but there are ways to make it a little bit more constant than this. But right now, you would be making, if you hooked up to that, you'd be making alternating voltage, and if it's connected to a circuit, alternating current. All right, that's what I need to tell you. Bye.